Hello students, this is Dr. A. Sayyed. I welcome you all for the course on matrix method of structural analysis. We are dealing with unit number 4, that is steepness matrix method for beams. Today in this class we will solve the last problem on analysis of beams using steepness matrix method. The highlight of today's problem is today we'll learn how to analyze the beam if supported by internal hinge using steepness matrix method. So the statement of problem is analyze the indeterminate beam as shown in figure using structure approach of steepness matrix method. The beam has fixed support at A and C. The beam has fixed support at A and C and has internal hinge at point B. Take EI constant. These are the given data. So this is given beam. If you look at the beam, support A, that is left support, and support C are fixed, and at point B, which is 1 meter from support A and 2 meter from support C, is internal hinge. The beam is subjected to UDL of 60 kN per meter full span UDL. Now since we have to solve this problem by steepness matrix method, we know that very first step in steepness matrix method is to find out degree of kinematic indeterminacy. So to calculate degree of kinematic indeterminacy, left support A is fixed support, and we know that degree of kinematic unknowns at fixed support is 0. So at A as well as C there is no kinematic unknown. So kinematic unknowns present only on internal hinge, at internal hinge support. Now because of this UDL, beam will deflect like this. Since internal hinge, it is an internal support, the point B will also shift vertically downward, means the point B is having vertical displacement, that is delta B, which is the first unknown. Now internal hinge is subjected to two unknowns, two rotations. Rotation of left portion of the internal hinge is different compared to rotation of right portion of the internal hinge. So left rotation is theta 1 and right rotation is theta 2, let us assume. So in short, total kinematic unknowns at internal hinge are 3. Those are vertical displacement, that is delta, and two rotations, rotation of left portion and rotation of right portion. And that's why if you look at the first step of the solution, dki equal to 3, delta b, theta 1 is represented by theta ba, that is b to a means left portion, and then theta bc means rotation of b to c portion, that is right portion. So dki equal to 3, first step. Now second step, we know that we have to find out various matrices which are involved in the compatibility condition, right? AD equal to ADL plus K into D. This is the compatibility condition. Already we have solved so many problems using steepness matrix method. So we know that this is compatibility condition. AD is equal to ADL plus K into D. So in this matrix, very first matrix is AD matrix. AD matrix stands for action corresponding to unknown displacement in the original structure. Action corresponding to unknown displacement in the original structure. First displacement is delta B, that is vertical displacement at point B. Corresponding action is vertical point load at point B. Vertical point load at point B or vertical force at point B. Okay. Second unknown is theta BA. Corresponding action is moment B to A. Moment B to A in the original structure. So in the original structure we have to see that is there any moment acting B to A. Similarly, third unknown is theta BC. Corresponding action is moment B to C. So like this, the action corresponding to three unknowns are vertical force or vertical point load at point B, that is action corresponding to delta B. Action corresponding to theta BA is moment at B to A, and action corresponding to theta BC is moment B to C. So in the original structure, if you look at the point B, there is no moment acting at point B in B to A direction as well as B to C direction. So both the moments are equal to 0. Similarly, since there is no vertical force acting at point B, the action corresponding to delta B is also equal to 0. So all three actions corresponding to three displacements are 0, and that's why all three elements of AD matrix are equal to 0. So this is first three elements are 0. Okay. Now second matrix in the compatibility condition is ADL matrix. ADL stands for action corresponding to unknown displacement in the restrained structure. So unknown displacement, again same three displacements are there. Delta B corresponding action is reaction at B. Force means vertical reaction. Then second unknown is theta BA. Corresponding action is moment B to A. And third unknown is rotation B to C. Corresponding action is moment B to C. So in short, in the restrained structure, we have to find out what is the reaction at B, what is moment B to A, and what is moment B to C. Those three actions will be the action corresponding to unknown displacement, delta B, theta BA, and theta BC. So restrained structure means now we have to fix all the supports. For simplicity, we have drawn two members separately, AB as well as BC. We have restrained all the supports, means fix all the supports. Both the span are subjected to UDL of 60 kN per meter intensity. First span is 1 meter, second span is of 2 meter. Now find out the fixed end moments. Since it is a UDL, fixed end moments are equal to WL square by 12 in both the span. So in first span, W is equal to 60 and L equal to 1. So W, that is 60 into L square 1, 60 into 1 divided by 12, answer will be 5. Fixed end moment are equal to 5 in first span. We know that left moment is always anti-clockwise, right moment is always clockwise. As per our sign conventions, anti-clockwise moment is positive, clockwise moment is negative. So it is plus 5 at A, minus 5 at B. Similarly, in second span, fixed end moments are calculated using the same formula, WL square by 12, because it is UDL, W equal to 60, L equal to 2. So 60 into 4 divided by 12, the answer is equal to 20, plus 20 on left support, minus 20 on right support. That is anti-clockwise at point B, positive, clockwise at C, it is negative. Now we have to find out the reactions in these two span. Reactions are calculated in two parts. First, reaction due to external load plus reaction due to moments. Reaction due to external load, since external load is UDL, reactions are equal to WL by 2. So W equal to 60, L equal to 1 divided by 2, 60 into 1 divided by 2, answer is 30. Okay, so both the reactions are 30. Similarly, in second span, similarly reactions are WL by 2. So 60 into 2 divided by 2, answer is 60. So these are the reaction due to external load. Now reaction due to moments. We know that already in previous 4 problems we had discussed how to find out reaction due to moments. Reactions due to moment are equal to sum of moment divided by span. Sum of moment, left moment is anti-clockwise means plus, right moment is clockwise means minus. In both the span, left is plus, right is minus. So what is sum of moment in first span? Left moment is plus 5, right moment is minus 5. Divided by span is 1. Sum of moment divided by span is the value of reaction. Since sum of moment plus 5 minus 5, this answer is equal to 0. It means there is no reaction because of moment. Similarly, in the second span, left moment is plus 20, right moment is minus 20. Sum of moment divided by span is 2. It is also 0. Plus 20 minus 20, answer is 0. There is no reaction because of moment even in second span also. So reaction calculation is over. Now we have to write down the ADL matrix. So in ideal matrix again, first element there will be three elements in this matrix. First element is corresponding to delta B, that is action corresponding to delta B is reaction at B. Then action corresponding to theta BA is a moment B to A, and action corresponding to theta BC is a moment B to C. Moment anti-clockwise is positive and reaction vertically upward is positive. So downward reaction will be minus and clockwise moment will be minus. Okay. So if you look at first element, delta B means action corresponding to delta B is reaction at B. What is reaction at B? Upward 30, upward 60. So both are upward. Addition of this 30 plus 60, answer is 90. Positive. Second element is action corresponding to theta BA is a moment B to A. So what is moment B to A? It is clockwise 5 means minus 5. And third is action corresponding to theta BC is moment B to C. Moment B to C is anti-clockwise 20 means plus 20. So 90 then minus 5 plus 20 are the elements of ideal matrix. Okay. Next step is to find out stiffness matrix of the given beam. And we know that stiffness matrix is derived by giving unit displacements one by one. Right. So there are three kinematic unknowns in our problem: delta B, theta BA and theta BC. So one by one we have to give the unit displacements. Okay, so first figure is delta B equal to 1. Let us assume delta B equal to 1. We know that we are always giving the displacement in positive direction. Since it is a delta, positive direction will be vertically upward. So we have to give vertically upward displacement at point B. So look at B point, we are giving the vertically upward displacement to this, that is positive. Okay, so the moment required to give the displacement in perpendicular direction, when member is horizontal and we are giving displacement in vertical direction, means it is perpendicular direction. So moment required to give that displacement in perpendicular direction is 6 EI by L square. This is value of moment, and this is same at both ends, same in magnitude as well as same in nature. So L is equal to 1 meter for first span, I equal to I, so EI equal to only EI, there is no change. So 6 into EI divided by L square means 1 square, so answer is 6 EI. It is same at two ends. Similarly, if you look at the second span, 6 EI divided by L square means 2 square, it is 4. 2 square means 4, the answer is 1.5 EI. Okay, answer is 1.5 EI. So these are the moments because of displacement in perpendicular direction. Now we have to decide the nature of these moments. Already we had discussed, but I will explain again how to decide the nature of moment. To decide the nature of moment, draw one arrow in the direction of displacement. Draw one arrow in the direction of displacement, that is vertically upward. Now bend that arrow outside the beam. Bend that arrow outside the beam, you will get the nature. If you look at this AB member, it is clockwise in nature. This is clockwise, so it is minus. So it is clockwise at support A also, it is minus. And in BC span, this moment is anti-clockwise. So anti-clockwise means plus. These two moments are positive. Okay, so minus in AB span and plus moment in BC span. Now since delta is one of the unknown in our kinematic unknowns, we have to find out reactions also. So to find out reactions, since there is no load in the beam now, we have to find out reaction because of only moments. How to find out reaction because of moment? It is sum of moment divided by span. Okay, so what is the sum of moment? Clockwise 6 EI and clockwise 6 EI. So minus 6 and minus 6 at A and C. EI is outside. EI is outside. Divided by span. Sum of moment divided by span. It is equal to minus 12 EI. Minus 12 EI. So this answer will be minus. Why it is minus? Because both the moments are clockwise, so minus. This minus answer represents that it is clockwise in nature. So to write down the couple because of reaction, that couple because of reaction must be of opposite nature, that is anti-clockwise. Okay, so anti-clockwise couple is represented by two unlike parallel forces like this. Left must be downward, right must be upward. So this is anti-clockwise couple. Left reaction is downward, look at this, left reaction is downward and right reaction is upward. This produces the anti-clockwise couple. Okay, so magnitude of reactions are 12 EI. Don't write down this minus in the magnitude. This minus decide that reaction couple will be anti-clockwise. Anti-clockwise means left downward and right upward. Okay, so these are the reactions due to moment in the first span. Similarly, in the second span, reaction due to moments. Now both the moments are anti-clockwise. These two moments are anti-clockwise in nature. Anti-clockwise means plus 1.5 plus 1.5. Sum of moment divided by span. 1.5 plus 1.5 divided by span is 2. Answer is equal to 1.5 EI. Okay. This answer will be positive because both the moments are anti-clockwise. So positive means it is anti-clockwise and therefore reaction couple will be clockwise. Clockwise means left upward and right downward. This is clockwise couple. This is clockwise couple. So left upward 1.5 EI and right reaction is downward 1.5 EI. Okay, these are the reaction due to moment in second span. So this is first figure of delta B equal to 1. From this figure we will get the first column of stiffness matrix. Okay, so first column of stiffness matrix K is equal to. Now understand, first element of stiffness matrix is corresponding to action corresponding to delta B. Second element is action corresponding to theta BA. And third element is action corresponding to theta BC. Right. First column will get from delta B equal to 1. Second column will get from theta BA equal to 1. And third column will get from theta BC equal to 1. There will be three columns corresponding to three displacements. So action corresponding to delta B is reaction at B. So here there will be RB. Action corresponding to theta BA is moment B to A. And action corresponding to theta BC is moment B to C. So these three forces we have to write down in stiffness matrix. So what is reaction at B in this figure? This is upward 12 EI plus upward 1.5 EI. The answer is 13.5 EI. Then moment B to A, this is the moment B to A. Clockwise 6 EI, so minus 6 EI. And what is the moment B to C? This is moment B to C. Anti-clockwise 1.5 EI. So this is 1.5 EI. Okay, so this is first column of the stiffness matrix. Similarly, second column you will get from the second figure, that is theta BA equal to 1. Theta BA equal to 1 means give the unit rotation at point B in A direction. Positive direction means rotation must be anti-clockwise. To rotate any joint in anti-clockwise sense, we have to apply moment in anti-clockwise sense. Since we are rotating only portion B to A, we are giving theta B to A equal to 1. It means there is no effect of this rotation on right portion of internal hinge. There is no effect of this rotation on right portion of internal hinge. It means all moments and reactions on the right portion will be 0. All moments and reactions on the right portion will be equal to 0. Okay. Now since we are rotating joint B in anti-clockwise sense, moment at joint B will be 4 EI by L. 4 EI divided by L is the value of moment at joint B, and 2 EI by L at joint A. Okay. 2 EI by L at joint A. L is equal to 1 meter for AB span. L equal to 1. So 4 EI by 1, the answer is 4 EI. And 2 EI by 1, answer is 2 EI. So 4 EI moment at point B and 2 EI moment at point A. Now we have to find out reaction due to these moments. So what is the reaction due to moment? Sum of moment divided by span. 2 EI is the moment at A and 4 EI is the moment at B. So 2 plus 4 EI is outside, divided by span is 1. Sum of moment divided by span. So the answer is equal to 6 EI. Answer is equal to 6 EI. This answer will be positive because both the moments are anticlockwise. Positive means anticlockwise. Positive means anticlockwise. So reaction couple will be clockwise. Reaction couple will be clockwise means left upward, right downward. Left upward, right downward. This is clockwise couple of the reaction. Magnitude is 6 EI. Okay. Now since there is no effect of this rotation on right portion, moments and reactions on right portions are 0. Okay. You please understand this is theta BA equal to 1. So there will be effect on B to A portion only. There is no effect of this rotation on B to C portion. Now we have to write down the second column of stiffness matrix. Second column means again same actions. Action corresponding to delta B is reaction at B. Action corresponding to theta BA is moment B to A. And action corresponding to theta BC is moment B to C. So what is reaction at B? Reaction at B is downward 6 EI, means minus 6 EI. What is moment B to A? It is anti-clockwise 4 EI, so it is plus 4 EI. And what is moment B to C? There is no moment B to C, so it is 0. Okay, this is second column. Similarly, we can write down the third column of stiffness matrix, that is theta BC equal to 1. Give the unit positive rotation in B to C portion. Positive means anti-clockwise. B to C portion now. We are giving the rotation on the right portion of internal hinge. So there is no effect on the left portion. So moments and reactions on left portion will be 0. Now since we are rotating B to C portion, 4 EI by L moment will be at B and 2 EI by L moment will be at C. So 4 EI by L is equal to 2 meter for this span. B to C span is 2 meters. So 4 EI by L is 4 EI upon 2 and this is 2 EI upon 2. Right. So 2 will get cancelled. This moment is EI and this 4 upon 2, this moment is 2 EI. Right. Now to find out reaction, it is sum of moment divided by span. 2 EI plus 1 EI. 2 EI on point B and 1 EI at point C. 2 plus 1 EI upon span is 2. 3 EI upon 2, answer is 1.5 EI. Okay. This answer will be positive. Positive means anti-clockwise. So reaction couple will be clockwise. Left upward, right downward. So it is a clockwise couple. So left upward 1.5 and right downward 1.5. These are the values of reactions. Okay. There is no moment and reaction in left portion because we are giving the rotation in right portion. Okay. So these moments will be 0. At the same time reactions will be 0. So final third column of stiffness matrix is first element is RB, that is reaction at B. Then second is moment B to A and third is moment B to C. Right. So what is reaction at B? It is 0 in left portion. It is upward 1.5 means plus 1.5 EI. What is moment B to A? There is 0 moment B to A. And what is moment B to C? It is anti-clockwise 2 EI means plus 2 EI. This is third column of stiffness matrix. So all these columns are combined and this is your final stiffness matrix. First column from delta B equal to 1, second column from theta BA equal to 1, third column from theta BC equal to 1. Okay, this is K. Once you find out the K, the last step is to write down the compatibility condition AD equal to ADL plus K into D. Okay, all matrices we have already determined. AD, all three elements are 0. This is from original structure. This ADL you will get from the restrained structure. This stiffness matrix you will get from the unit load figure, and this D stands for vector of unknowns. Okay, if you solve these three equations, 3 unknowns in your calculator, final answer of 3 unknowns, delta B is equal to minus 20 upon EI, theta BA equal to minus 28.75 upon EI. This minus rotation represent it is clockwise, and this minus delta B represent it is downward. Positive rotation theta BC represent it is anti-clockwise. Okay, these are the final kinematic unknowns, and this is how we can account the internal hinge in the solution of problem using stiffness matrix method. Okay, please understand again, when you provide the rotation at any point B in a internal hinge, if you give the theta BA equal to 1, that is rotation of left portion of the internal hinge, there is no effect of that rotation on the right portion. At the same time, if you give the rotation to the right portion of internal hinge, there is no effect of that on the left portion. Okay, moments you can calculate using the similar procedure what you already used in the previous problems. Okay, so this is fifth problem on the stiffness matrix method for beams. I hope all of you have understand the structure approach of stiffness matrix method. In the next class we will start member approach of stiffness matrix method for the analysis of continuous beams. Okay, thank you very much.